This is a revision video for AQA GCSE Chemistry or Combined Science Unit 10, Sustainable Development. You can download the questions from the link in the description and then use these to check whether you've learned the key content before moving on to questions where you apply or analyse this information. There's lots of opportunity in this unit for questions where you need to do that. Humans require resources for warmth, shelter, food and transport. There are obviously lots of other things as well, but those are the four that are listed in the specification. So if it's a multiple choice question, they're the four that you're looking for. Finite resources are ones that are running out faster than we can replace them, whereas renewable resources are things that we can replace at the rate we're using them. Synthetic resources are things that we've manufactured from chemicals, and they tend to be more durable for a lower cost. Potable water is water that is safe for us to drink. And it's distinct from pure water because pure in chemistry means that there's been nothing else added to it. It's one element or one compound. So potable water can contain other substances, just not dangerous ones. Water might not be potable anymore if it contains high levels of salts, toxins or pathogens. Here in the UK, to make potable water, we need to find an appropriate source of fresh water, then filter it to remove any solid objects, and finally sterilise it. That could be by using UV light, ozone or chlorine gas. The point of sterilising it is to kill pathogens. It's important that you're saying kill rather than remove, because actually there could be bacteria in the water you're drinking. It's just they're dead because we've killed them with chlorine. Desalination is what you need to do to seawater before you can drink it. It's removing salt. So the easiest way to remember this is that saline solution you might have used maybe if you've had your ears pierced, and that's basically salty water. You can make it yourself by boiling up some water and adding salt to it. So desalination is stopping water from being saline. Two methods for removing the salt from the water are distillation, where we heat the water up until it evaporates and then condense it back into a liquid, and reverse osmosis, where very high pressure is used to force the water through a partially permeable membrane so that the salt is left behind. These methods are rarely used if fresh water is available because they're both very energy intensive and that makes them very expensive. If we're using agricultural wastewater, which comes from farms, then we're going to need to remove organic matter and also sterilise it again to remove more harmful microbes. If we're using industrial wastewater, so from chemical factories, again we're going to need to remove organic matter and we may need to remove harmful chemicals. If we're making potable water from sewage, then firstly we need to do screening and grit removal. Then there's a sedimentation step to produce a sewage sludge blanket and effluent. Then there's anaerobic digestion of that sludge blanket. And then there's aerobic biological treatment using bacteria of the effluent. This next slide is just for people taking higher tier only. An ore is a rock containing enough metal compound to make extracting it financially viable. We're starting to need to use alternative methods to extract copper because high-grade copper ores are running out and the demand for copper is very high because it's so scarce. Phytomining is one example of an alternative method of extracting copper and other metals, and it's using plants. So basically the plants are planted in a field that's been contaminated with heavy metals like copper, and as they're absorbing water, they're also going to absorb these copper ions. Bioleaching is a similar system, but instead of using plants, it's using bacteria. The solutions that we get from phytomining and bioleaching can then be processed by using electrolysis or displacement using scrap iron. In order to get the solution from the plants, what we actually do is we burn those plants that have been used in phytomining, and then we can dissolve the ash using acid. A life cycle assessment is an assessment of the environmental impact of a product, and there are 4 stages to it, which are looking at the extraction of the raw materials, the manufacturing of the product, the operation and use throughout its lifetime, and finally the disposal. And in each case we want to know what materials are being used, what energy is being used, what pollution is being produced, and so on. It's really hard to actually assign a financial numerical value to pollutants because it's very hard to know exactly what pollutants have been produced. So for instance, if you think about a computer, a lot of the pollution that's associated with using that computer is from the electricity to run it. But you don't actually know how that electricity has been generated. It could be from a coal power station, it could be from a nuclear power station, it could be from a wind turbine. You've just got no way of knowing. Companies can misuse an LCA because they write them themselves. So often they can be selective or abbreviated, they can miss out information. And so they can use that when they're advertising a product to say, oh, this is great for the environment, when actually it's not impartial and they've kind of put biased information in there. We can reduce the use of limited resources by reducing how much we use, reusing things after we've made them, and also by recycling them. The 5 materials listed in your specification are metals, glass, building materials, clay ceramics, and most plastics. There are obviously a ton of other examples, but those are the ones that the exam board lists, so those are the ones you need to know. To recycle glass, we crush it and then we melt it, whereas metals get melted and then either recast or reformed. 2 things that influence the amount of separation and processing that's required for recycling are the material we're using and also the properties that are required of the final product. So for instance, if I'm recycling plastic and it's going to be used for something that's not really on show, then the colour isn't going to matter. But if I'm using it to make milk bottles, it's really, really important that I'm only putting clear or white plastic in there. Because if I get, say, some green plastic mixed in, I'm going to end up with a slightly green milk bottle, and nobody's going to buy milk in a slightly green milk bottle. The last 30 or so questions are just for people taking GCSE chemistry or what you might call triple science. So if you're taking combined science double award, you can stop watching now. Corrosion is defined as the destruction of materials by chemical reactions with substances in the environment, like oxygen from the atmosphere. Rusting is the name that we give to the corrosion of iron, and this requires both oxygen from the air and water. So this could be put in the context of a question which asks you about how you could stop something like an iron nail from rusting. So you could have a series of different experiments which are either going to stop oxygen getting in or stop water getting in, and look at which of these is going to rust fastest. 5 ways that we can stop corrosion are by greasing, so literally covering something in grease so that oxygen can't get in, painting for the same reason, electroplating, where we use electrolysis to stick a thin layer of a different metal that's not going to react over the top. Aluminium will naturally form a thin layer of aluminium oxide around the outside, and that is very hard and very resistant to reactions. So even though aluminium is actually quite reactive, that aluminium oxide protects it. And finally, galvanizing, which is where you mix the metal with another metal that's more reactive, like for instance zinc. So zinc can be used to protect iron by galvanizing it in what's basically called a sacrificial method. So zinc is more reactive than iron, and so any oxygen in the atmosphere will preferentially react with the zinc. But whereas iron, when it oxidizes, becomes all sort of flaky and will break apart, zinc oxide isn't going to have that same effect. So even though the zinc is being oxidized, it doesn't threaten the overall integrity of the metal. Copper is less reactive than iron, so it doesn't matter if you mix it in there, the oxygen from the atmosphere is still going to react with the iron because it will always react with the more reactive metal. An alloy is a mixture of metals, or a mixture of a metal with another substance like carbon. Bronze and brass are both alloys of copper. In the case of bronze, it's copper alloyed with tin, and in the case of brass, that copper has been mixed with zinc. When gold is made into jewellery, it's often alloyed with silver, copper and zinc, and this is going to make it a little bit harder. The carat system is used to describe how pure gold is. So 24 karat gold is pure 100% gold. And if you say that a ring is made of 18 karat gold, well 18 is 75% of 24, so that tells you that 75% of that metal is actually pure gold, and then the other 25% will be other metals like silver or copper or zinc that have been added to make the gold harder. High carbon steel is strong but brittle, so it's useful for making things that need to be very, very hard and don't need to have their shape changed, so say drill bits. Low carbon steel is softer, so it's better for making things like car bodies that need to be bent into a particular shape. Stainless steel is also very hard and it's resistant to corrosion, so it's useful for things that are going to be in contact with, say, acids. Aluminium is great because it's very, very low density, it's very, very lightweight. So for things like making drinks cans, it's useful because it means that when you're transporting thousands and thousands of cans of, I don't know, Coke, you're not paying for lots of fuel because of the energy it takes to transport something very, very heavy. Bronze is used for making coins, like 2p pieces. Brass is used for making the pin plugs and electrical plugs. Aluminium alloys are used for making aircraft because, as we've said, they're very, very lightweight, so it means that the plane is going to need less fuel than if it was made out of, say, steel. High carbon steel is used for making cutting tools. Low carbon steel is used for making car bodies because it's softer, it's more malleable, it's easier to shape into the shape of the car. And stainless steel is used for making cutlery because it's less likely to corrode when it comes into contact with the acids in the food and things like that. Soda lime glass is made by heating up a mixture of sand, sodium carbonate, hence soda, and limestone, hence lime. Borosilicate glass is made by heating a mixture of sand, which contains silica, and boron trioxide. And the advantage of borosilicate glass is that it melts at a much higher temperature. So all of the glassware that you've used in your chemistry lab is going to be made from borosilicate glass, so that when you put it in a Bunsen, it doesn't just suddenly start melting. Clay ceramics are made by shaping wet clay and then heating them in a furnace or a kiln until they dry out. The properties of polymers can be influenced both by the starting monomer, so what we're actually making it out of, and the reaction conditions, so things like the temperature the polymer is made at, the pressure it's made at, and whether or not a catalyst is used. The difference between thermosoftening polymers and thermosetting polymers is that thermosoftening polymers will soften when they're heated, whereas thermosetting polymers won't. They'll just eventually start to char and burn. This is the case because thermosoftening polymers are just made of individual polymer chains which aren't bonded together, whereas thermosetting polymers have got strong crosslinks between the chains, which are actually covalent bonds. A composite material is made from two parts. There's a matrix or a binder which is surrounding fibres or fragments of what we call the reinforcement. So an example of this could be steel reinforced concrete. There are bars of steel and then they're surrounded by a mass of concrete. And so this gives it different properties. So for instance, when you try to squash it, the concrete will resist, and when you try to stretch it, the steel will resist. The purpose of the Haber process is to make a compound called ammonia, which is really, really useful for making fertilisers and things like that. The equation for the Haber process is nitrogen plus hydrogen and then a reversible reaction arrow to make ammonia. The raw materials are obviously nitrogen and hydrogen, and we get this nitrogen from the atmosphere around us, and the hydrogen can be made by a chemical reaction of methane, usually with steam. The reaction conditions for the Haber process are an iron catalyst at about 450 degrees C and about 200 atmospheric pressures. These conditions are a trade-off between the conditions that will give us the highest yield and the conditions that will give us the fastest reaction. So, because it's an exothermic forward reaction, the biggest yield would be if we actually had a really, really low temperature. But unfortunately, having a really low temperature would make the speed of the reaction so slow that it just wouldn't be worth doing it. So the temperature that we use is a compromise between the highest yield and the fastest reaction. Increasing the pressure is both going to speed up the reaction and increase the yield of ammonia, but also if the pressure gets too high, it gets very expensive and also quite dangerous. So we stop at about 200 atmospheric pressures because that's going to give us a reasonable yield and a reasonable speed, but it won't be too dangerous. And then because the reaction is quite slow still, we use this iron catalyst to speed it up. Once the ammonia has been produced, it's still mixed up with lots of other gases, the nitrogen and the hydrogen. So the whole mixture of gases is cooled down below the boiling point of ammonia, but above the boiling point of hydrogen and nitrogen. So it's sort of like fractional distillation, but in reverse compared to how you're used to it with crude oil. What this means is that the ammonia turns back into a liquid and it can just be sort of tapped off, whereas the nitrogen and hydrogen can be recycled back round into the reactor to be used again. An NPK fertiliser is a chemical used, it's sprayed on crops to help them grow better and make more protein, and it contains the three elements indicated by N, P and K, so nitrogen, phosphorus and potassium. To get the salts that contain the nitrogen, phosphorus and potassium, we use ammonia to make ammonium salts and nitric acid, which contain nitrogen. Potassium chloride and sulfate are both present in rocks and they can be mined, and those salts can be used directly. And then phosphate rock can also be mined, but you can't just use it directly in the fertiliser. So it needs to be either treated with nitric acid or sulfuric acid to make soluble salts, which can then be used in the fertiliser. I hope that was helpful. Don't forget to subscribe.